As promised, here is part 2 of lesson 4.4. We're going to talk about the intersection of two planes. Planes. I have to have some fun. I'm sorry. I'm just messing with you guys. Okay, so I'm actually pretty proud of this lesson, mainly because I somehow was able to make some pretty awesome diagrams, and I used Word. I'm not very techy. I don't know how to use like media arts and things like that, media programs. So I'm going to pat myself on the shoulder there just a little bit. Let's do a quick recall. So how do two lines interact in 2D and 3D space? There are 4 cases. And so case 1, 2, and 3 exist in 2D and 3D space. But case number 4 only exists in 3D, and that's the one with the skew lines. Okay, now I challenge you to pause the video and think about how 3 lines intersect in 3D space. I know, mind blown, right? But this is like some higher level thinking here, and I think that there are about 8 different cases. I know. All right, so moving on. If we interact a line and a plane together, we get 3 different cases, first of which has no intersection, like 0 points of intersection, because they are parallel and distinct from each other. Case number 2 is where we have infinite number of points of intersection because that line is lying right on that plane. And so these guys are parallel and coincident. The third case is where we have 1 point of intersection, and that is where the line and the plane are not parallel, and so they do interact and they do intersect, and so that line is going to pierce right through that plane. Okay, so now that we've talked about lines and lines, lines and planes, obviously we're going to talk about 2 planes, so planes and planes. Think about 2 pieces of paper and how they could possibly interact with each other. Okay, so here are my fancy diagrams. All right, so the very first case, you can have them as parallel and coincident, where you have 2 pieces of paper or 2 planes and one lies right on top of the other. And so they're touching all the time. This one has infinite number of solutions. Okay, so infinite number of times where they intersect each other. If you take a look at their normals, now remember the normals are these perpendicular vectors to each of the planes. This one's perpendicular to the green plane. This one is perpendicular to the blue plane. If both of the planes are parallel to each other, it must mean that their normals are also parallel to each other. And so that might be something that we would want to check because it might, eliminate one of the cases. Because, if you take a look down here, this second case also has both of the normals being scalar multiples. That means that these 2, even though they're not coincident planes, and they're actually distinct planes, since they're parallel, the normals are also parallel. Okay? Now, if we take a look at both 1 and 2, case 1 and case 2, you'll see that they, even though they are quite similar in that first condition, they actually are different in terms of the number of intersections. And so the second diagram has no points of intersection because they're parallel and distinct. They actually don't touch at all. Okay, and so there are no solutions, whereas this one's solutions are infinite, but their solutions are where they touch. And so where they touch is in the shape of a plane. Okay, so your answer might be in the form of a plane. I'll show you more when we get into some of these examples. Now, the very last way that they can touch is if they were kind of slicing through each other. And so where they touch is along this line. And so your answer will take the form of a line, and you still have infinite number of intersections because there's infinite number of points all along that line. Notice though that their normals, so this one, I don't even know how to draw this. How would you, like something like this, I guess? That would be normal number 1. And then normal number 2 might be going like this. So notice that their not scalar multiples of each other. That means that I think maybe if we were to try to eliminate one of this, like the cases, I would probably try to eliminate this one first by checking out the normals of both of the planes and seeing if they're scalar multiples. And then what I would do is maybe for these two, I would say, well, if there's a point on this plane and it actually does not exist over here, then that means that we must have distinct planes. Whereas if we have a point that exists on the plane, but it also exists underneath, like on the other plane as well, then it must be coincident. So like I said, let's go over some examples. I'm going to be going over them quickly, so I'm sorry, but I do have quite a couple examples for you, and I'm hoping that the colors help. All right, so we have two planes. They're both in scalar form. Let me just go away. Okay, scalar form. And so when they're in scalar form, it actually makes it a lot easier to see everything that's happening, like the normals first of all. Okay, so as you can see, the normals are in the front, right? Okay, so I have both of the normals, and I can first of all check if they're even parallel by seeing if they're scalar multiples. And so I'm noticing that if I double the normal 1, I'm going to get the second normal. And you can see that already, like 3 doubled is 6, 2 doubled is 4, 4 doubled is 8. And so we can actually tell if they're the same plane, like they're coincident, if you also compare the d values and see if it also doubles. And that's what this is saying down here. So there's actually two different things that we can do. We can either do this one, or we can do this one. So I'm just going to talk about the bottom one first because it does make a little bit more sense. And so if you see the -7 doubling to become the 9, then that means that they're both coincident, but obviously 7 doubled is not 9. Okay, so we make this statement and then we say they're parallel and distinct from each other. Another way that you can do this, and so if you can separate these two and you can do the top instead. So the top actually encompasses all that. Okay, so the top is what we had said at the beginning. If I just find a point that is on the first plane, like if I just say x is equal to whatever and y is equal to whatever, I can solve for a z value in order to find a point that is on plane number 1. Once I have that, I can then substitute it into plane number 2. So take a look at step 3, where I put P into plane 2, and I just check to make sure that the left side is equal to the right side. It looks like it isn't. We have 23 over here and 0 over here. So that means that that point does not exist on plane 2, and that means that they're actually, both planes are distinct from each other. Okay, so let's take a look at the next one. All right, example number 2 is saying, how do these planes intersect? And by the way, they're always going to start like that. They're not going to give you any clue. They're just going to be like, okay, which of these 3 cases do we have? Include a full analysis. And so the very first thing we're going to do, again, we're going to check out the normals. And so we have 3, -1, and 4 for this guy. We got 1, 1, and -2 for this guy. And taking a look and seeing if they're scalar multiples, it doesn't look like it, does it? Okay, so that means that they're not parallel, which means we only have the third case, and that was a case where they touch infinite number of times, and your answer should look like a line. Okay, so first of all, if they touch, you have to do some sort of substitution elimination, right? Okay, so doing substitution or elimination will get you the point of intersection, or in this case, the line of intersection. So what I'm going to do instead of substitution elimination, because it takes a lot of space, is I taught you in the last video how to do matrices, like how to use matrices in order to find your x, y, and z. okay, in just like a shorter way. So I'm going to do the same thing. I'm going to put all of my coefficients from my normal into one row, and then putting all of my coefficients of my normal for my second plane into the second row. I'm also going to include the equal sign, making sure that my constant is on the other side. Okay, so notice that you have a positive 7 and a negative 5. Oh, and there's my equal sign, just in case you forgot. Okay, so you can follow all of the steps. I'm not going to go through this again because I did in the last video. But basically, your goal is to make sure that you have those diagonal ones and you're putting them into row-reduced echelon form. Okay, so you want those zeros above and below the ones. What you'll notice is that we didn't really solve for any equation because, or any variables, I should say, because, let me get rid of those. What this means is you have 1x, 0 y's, a half a z, and that's going to equal to 1/2 if I put those all together. Okay, so that's what's right here in row 1. This guy at the bottom is saying that you have 0 x's, 1 y, negative 5 over 2 z's, and that's going to equal to negative 1, so negative 11 over 2. And that also didn't really solve for a variable, did it? That's going to be my row 2. So what we do in this case is we sub in any letter that we want in as our z, because z, it looks like, is what will dictate what x is going to equal to, and it'll also dictate what y is going to equal to. And so since we don't know what z is, we'll just let it be something. Let z be anything. You can just say k, you can say t, whatever you want. And we're going to sub it in right here, and we're going to get x by itself. Okay, we're going to do the same thing, sub k in for z over here, and then you're going to get what y equals to in terms of k. So taking these two equations, you're now going to set up your line. All right, so first of all, it looks like a point of intersection where we have x, y, and z, and you know that x is my first red box, so 1/2 minus 1/2 k. My y is the second red box, negative 11 over 2 plus 5 over 2k, and then you had let z equal to k before in blue on the right-hand side. Now that looks like a coordinate, but we're just going to rewrite it as a vector line. Okay, so we have our k parameter right here, and so every number in front of the k is my direction vector. Every number that isn't in front of my k is going to be my position vector, okay, or your point. Now, putting it into the final form, what I have is do not reduce your point. You're not allowed to. Okay, so that's going to stay as is. Don't touch that, but you can always make this look a little bit prettier. Remember how we said the negative is not something that we really, really want? And so if you don't want a negative and you don't want the fractions, what you can do is multiply this entire bracket. You remember how we factored out something before? Well, we can multiply something as well. If you multiply that entire thing by a scalar, and what I usually use is a common denominator of all your fractions. So it looks like your common denominator is probably 2. And since I want to get rid of that negative in front of the half, I'm going to multiply everything by negative 2. Okay, so that's my scalar, and that'll give you a nice clean direction vector without any negatives and without a negative first number and without any fractions. All right, let's go over some more examples. Number 3. So number 3 is saying we're again given 2 planes, and let's just check them out. We have 3 possible cases. So take a look at the normals first. 3, 2, and 4. I don't know why I made that one squiggly, but that's okay. Then we're going to look at the next one, 6, 4, and 8. Oh, okay. It just looks like the first one is like half as big as the second one, right? because we can divide the second one by 2, which is a scalar, and we'll get the first normal. That means that they're parallel. And so we have case 1 or case 2, they're either parallel and distinct or parallel and coincident. That means that what I'm going to do is I'm just going to compare the d values, because if I multiply this entire thing by 2, will I get the second plane? Because if I do, that means that they're actually coincident. And it looks like when I compare the d values, yeah, if I just double this as well, I'll also get the same number, -14. Okay, so since I can double the entire first plane and get the entire second plane, that must mean that they are parallel and coincident. Okay, going on to B. What I want to do first is they're not obviously in the forms that I like. And this is what makes these questions really tough, is when they don't put it into the form that we like, we got to spend all that time putting it into the form that we like. So, ugh. Anyways, okay, let's take a look at the first one. Convert it into scalar form, okay, because I can't really see my normal right now. What I'm going to do is I'm going to take my two direction vectors and cross them to get my normal vector. Then I can take my normal and put all of the numbers into my coefficients in front of my x, y, and z. The reason why we put this into scalar form is because I can compare my d's. And if my d's are just like in 3a, the last question we just did, if they're like a scalar multiple of each other and it's a parallel situation, then I can say that they're coincident. Okay, so what I'm going to do is I'm going to plug in my 2, 1, and -5 into my plane, because obviously it exists on this plane, and I'm going to get plane 1. I'm going to do the exact same thing with plane 2, cross both of the direction vectors, and sub in my point to find the scalar form of my second plane. Okay, so that is right here. All right, so I have my normal after I've done the cross product, and then I subbed in that point right there, and I got my d value. Okay, so now that I have a purple plane in scalar form, I have an orange plane in scalar form, there are two ways that we can do this. We can first of all do this algebraically, and we can compare the normals. I see that they're scalar multiples. That means that they're parallel. And then I can also compare their d values, which doesn't really look like they're scalar multiples, does it? And so since the d's don't really match, that means that they're parallel, but they're distinct from each other. Or I can use matrices. Okay, and so what I can do is I can put each of the planes into rows of a matrix. I can row reduce into row reduced echelon form. And you'll notice after you show all the steps that something is going on right here. And so 0x, 0y, and 0z is equal to 1. That doesn't even make any sense. How can 0 equal to 1? And since that doesn't exist, like no x, y, and z possible numbers could ever make that equation equal to 1, that means that there are no intersections, or we would say that both of the planes are parallel and they don't touch each other, and so they're distinct from each other. In the last example, I think it's last example, this is example number 4, and again, same thing, except now they want us to create a third plane. Okay, so they're saying that the first two planes intersect in a line. Maybe we should actually find that first. Okay, but they want us to create a third plane. It passes through P and Q, and it also passes through that line. So I think we're going to have to find that line first. You guys know how to do this. First of all, compare the normals. Okay, then you're going to compare the d values. Since they're not scalar multiples of each other, they're not parallel, which means that obviously we'd already said it intersects in a line. Okay, so we're going to have to solve for that line, and I would probably use matrices. Once I get it into row reduced echelon form, I can then create two equations. And so I have from the top purple this equation right here. From the bottom orange, I get this equation right over here. Letting z equal to any number, so I'm just going to call it t. Last time I used k. It doesn't really matter what letter you use. Okay, we're going to make it into a scalar, so we're going to just use t for our parameter, I guess. And we're going to sub it into wherever you see a z, because depending on what z is, x is going to change and y is going to change. And so what you want to do is sub in that t and then write down the equations in the form of t. Okay, now what you're going to do is you're going to rewrite that into, maybe I scrolled a little bit too fast. Okay, going back here, we're going to rewrite those as your direction vector for your x, direction vector for your y, and then remember you had said that z is going to be 1t, and so that 1 is going to be your direction vector for the z. Okay, now whatever is in front, this guy, and, well, there is no guy, so that's 0, is going to go right here as our position vector, or our point. Don't reduce the point, you're not allowed, but you can maybe multiply all of this to get rid of the fractions. Maybe I would multiply by a negative common denominator of 7, and that will get rid of the negative at the very front and then also all the fractions. Okay, so you get a nice direction vector, and this is our line, our vector equation of a line where we have infinite number of intersections between these two planes. So they had said create a third plane because we couldn't make this question difficult enough. Let's just throw in something extra there. Find an equation of a third plane. It has to contain P, Q, and this line. And so what I did was I said, okay, we need this direction vector. That's part of the plane. When you make an equation for a plane, you need two direction vectors. So why don't we make another direction vector by taking P and Q? So we're just going to subtract OQ and OP. All right, and we're going to get a new vector. Now, taking those two vectors, A vector and B vector, okay, so I don't really care about this. I care more about that. Putting parameters in front of them, whatever letters you want, as long as they weren't used before, and then choosing either P or Q and putting that in as our point. We then have an equation for a third plane, and that is it, folks. Can breathe a little bit. Okay, I'm sorry if I went through that really super quick. Definitely ask questions if you need to, but I think logically a lot of this hopefully makes sense to you. But I think what would be a really great idea is going through each of the examples and coming up with a pattern. What is a pattern that we can use in order to solve every single question? And that way we don't have to memorize what to do in each question. Do you guys notice that I don't really know what to say at the end of videos? See you later.